In this video, we're going to be looking at a topic for Chapter 5 called Points of Concurrency. And I'm going to be showing you some stuff in OnShape, which we've looked at before. Um, this is not like a district endorsed product, but it is a really good free CAD program, and they have free accounts for educators and students. So if you're interested in following along with what I'm doing, you can go to onshape.com and create a student account, and it's completely free. You do have to sign up for it though, so if you don't feel comfortable doing that, that's not a problem. I'm going to go through this, but it is a really neat tool to be able to do some of the stuff that we're talking about in geometry. So starting out, I want to look at just an idea of what we can do with 3 points. So we know that 3 points can create a plane, and then within a plane, if I were to make a sketch, 3 points can define a triangle. So anywhere I put these 3 points, if I connect them with line segments, then I end up with a triangle. And we've seen before in Chapter 4, we can move these points around anywhere we want and create any triangle in existence. So by having the freedom to move those points, we can make triangles. But I want us to consider if we can make something else with 3 points. Will you let me pick the line? There we go. So looking at the origin, what would we think if I were to put the 3 points kind of like here around the origin? You can kind of see that if they're all the same distance away, that would be like a radial distance, and what we could end up with is, instead of a triangle, we could end up with a circle that goes through those 3 points. And what I wanted to get at first is we can create a circle with any 3 non-collinear points, just like we can create a triangle. So it doesn't matter if they're equally spaced around this origin, the center of a circle could be anywhere. So I'm going to create a circle, not using its center like we normally do. So this is a center point circle where we pick the middle and then pick a radius. The other way to draw a circle is called a 3-point circle. So with 3 non-collinear points, we fully define the center and radius of a circle. So with those 3 points now, no matter where I move them, I have this circle to where these 3 points are on the circumference of it. So if I put the points really close to being in a straight line, then we end up with a very, very big circle, because if they're that close together, then we must be at a very flat part of the edge of the circle. Whereas if I move them kind of away from each other, the center is now between them, like that. So a lot of what we're going to talk about today is going to revolve around triangles and circles, so I just wanted us to have this understanding that a circle can also be defined by 3 points, just like a triangle can. So now we're going to look at what we call special segments in triangles. There are 4 main kinds of special segments that we're going to look at. We're going to start with this one. So this one, we have 3 segments that are perpendicular bisectors of the sides of the triangle. So what that means is this line, this construction line here, is cutting perpendicular through this side of the triangle and is splitting it exactly in half. So it's perpendicular and it's a bisector. We have 3 of those, and when we put all 3 of them together, they're going to meet at a single point called the point of concurrency. So concurrency is just a spot where 3 or more objects intersect. So it's like an intersection, but for 3 or more things. So this point of concurrency here is the intersection of these perpendicular bisectors. So this section, this chapter, is short, but it has a lot of vocabulary. So these lines are perpendicular bisectors. We already knew about those, so hopefully that's not a new vocabulary. And the point that they create right here is called the circumcenter. So center sounds kind of like a circle, and so does circum, right? It sounds like circumference. So why is it called that? Let's take a look at what happens as we change our triangle. So as I move my triangle, that circumcenter moves around. And if I have an acute triangle like this, the circumcenter lies inside of the shape. But if I make it an obtuse triangle, so this is going to be a 90-degree triangle right here, and then the circumcenter is on the hypotenuse. But if I keep going and make an obtuse triangle, the circumcenter moves out of this triangle and moves further and further away. So notice that as I'm doing this, these 3 points making the triangle are getting more and more into a straight line. And we saw that with circles, the more we make the 3 points in a straight line, the further away the center of the circle moves. So there's something going on here with that if we make a 3-point circle with the 3 vertices of the triangle, the center of it is this point where the 3 perpendicular bisectors meet. So that's why it's called a circumcenter, is because this circle, we use the term, it's circumscribing the triangle. So circum means around and scribe means drawn. So it's a circle drawn around the triangle. So I think of it as being like circumference, so the points of the triangle are on the circumference of the circle. And so a few things about this we should probably know is that since the circle, or since each vertex of the triangle is on the circle, that means that from the circumcenter to each vertex is going to be equidistant, because those are all radii of the circle. So if I draw this distance, and this distance, and this distance, let's measure those. So it doesn't matter what they are, I just want to know that they're the same. So 6.20522, 6.20522, 6.20522. So all of those distances from the circumcenter to the vertices are the same. Meaning if we know where the circumcenter is, and we know the distance to one vertex, we know the distance to the other vertices as well. So that's a mathematical relationship that comes out of the circumcenter, is that all of the vertices are equidistant from it. So yeah, that's our first kind of point of concurrency called the circumcenter, created by perpendicular bisectors. And the mathematical significance is that it's equidistant from the vertices. So let's move on to our second point of concurrency. This one, I already have the circle drawn. And what we've done here, let's go ahead and undraw the circle. I don't want it. What I've done here is drawn the 3 angle bisectors. So in the last shape, we bisected the sides perpendicularly. This time we're bisecting the angles. So each of these construction lines goes from a vertex to the opposite side, and I have it set so that the 2 half angles here are equal to each other, so that I know I'm cutting it exactly in half. So to see that, we could see this is 15.4427707, and this is 15.4427707. So I've set up the geometric constraints so that all 3 corners are bisected. So no matter how we move this triangle, these lines will always be bisecting those corners. Yeah, so that's what this shape is. So we're creating a point of concurrency here by the angle bisectors. So our special segment type here is angle bisector. Our point of concurrency is called the InCenter. So the reason for that is we have a triangle, or sorry, a circle that's centered at this point of concurrency, and it's going to be what we call tangent to all 3 sides of the triangle. So I'm going to use this constraint here called tangent. That's a term we haven't seen yet in geometry that means a curve that touches at only one point. So it means that if I make this circle tangent to this line, they're going to touch at one point, kind of like on a parabola where the vertex hits and then turns around and goes the other way. So similar idea to that. I'm going to make it, this should be tangent to all 3 already. So when I made it tangent to one, the fact that its center is here, it was tangent to all 3 of them. So no matter how close I zoom in, there's going to be exactly one point where they touch. So I can't zoom in infinitely far, but that's the idea, is that it touches and then immediately goes away from it. There's not like an area of overlap. So we call this point the InCenter, because this circle, the term for it is that it is inscribed within the shape. So inscribed means it's drawn inside of the shape rather than drawn around the shape. So the circumcenter, or circle, I guess, was drawn around the triangle, and the incircle, which has this InCenter, is drawn inside the triangle. So what is its mathematical significance, right? So that's the thing we want to get at, is what segment creates this, then what is it, like conceptually what's happening, and what's its name of that point of concurrency, and then lastly, what does it do mathematically? So this one, since it's basically, think of again this circle, every point on it is equidistant from the InCenter, meaning if I go the minimum distance to any of the sides, right? So if I go to this side, we talked about minimum distance being perpendicular to that side, right? I could go a really long way like here, or even like here, right? This isn't the minimum distance, that just happens to follow along this angle bisector line. So the minimum distance from here to the edge here is going to be, well, I'll just draw it, and then I'll force it to be perpendicular. So this is perpendicular to that. Of course. That's fine, it actually worked. So now this line from the InCenter to any edge is going to be the same distance, because all of them are a radius of the circle. So let's draw this one to this edge. There's perpendicular right there. And then let's draw this one perpendicular to this right there. So since all of those are radii of this incircle, that means that they're all equal length. So 1.97581, 1.97581, 1.97581. So if we have the InCenter, then we know the distance to each side, the minimum distance, is the same. Or you could think of it as the perpendicular distance to each side is the same. So that is this one. As a recap, our segment type was angle bisector. Our point of concurrency was the InCenter. And then the mathematical significance was the minimum distance from the InCenter to each side, or the perpendicular distance, is congruent. So we have the same distance to all three sides. So those are our two that have like a circle around the triangle, a circle inside the triangle. But there are other relationships that we can come up with too. So there's other kinds of special segments. This one I've drawn from each vertex to the midpoint of the opposite side, meaning that I've split this side in half, kind of like I did with the perpendicular bisectors. The difference is, instead of this segment being perpendicular to the side, it connects over to the other vertex, the opposite vertex. These lines are called medians because they basically go to the middle of the opposite side. So these three medians have a point of concurrency here, and there's not like a circle that does anything with this one, but it is a really important point. This one actually, outside of geometry, as you go into like engineering, is probably the most important one. We call this point of concurrency where the medians intersect the centroid. So that's C-E-N-T-R-O-I-D. We also call it a center of mass or center of gravity. So when you have an object, like if you have something, any object that you're holding, there should be a spot you can hold where it's going to naturally balance. So think of like putting your finger under a plate or something. There's a spot where if your finger is in just the right spot, it's going to balance over that point. And that's what this is. This is that balancing point, assuming that this triangle is all the same density, so it's not like heavier on one end and lighter on one end. Then this is the point where it's going to perfectly balance. It's like the geometric or math, like it's the center of, it's really the center of the object, but all of these in a way are centers. So this to me is the center of the triangle. So what is its mathematical significance? It's always going to be located 1/3 of the way along from the edge to the vertex. So if we're going from this side toward that vertex, it's 1/3 of the distance. Or if we're going from the vertex to the centroid, that would be 2/3 of the total distance. So let's put a dot here and measure to see how that works. So we're going to check here to here is, and we don't want the vertical distance, we want the inline distance like that. Let's go ahead and make it 5, just so we'll take that away later, but just so we can easily compare, we can see, actually I should have made it 10 because 5 is odd. Let's make it 4. So if that's 4, then this one is 2, right? So it's the total length is 6, and it's 1/3 of the way from the edge, or 2/3 of the way from the vertex. So if we know the centroid, then that gives us a relationship where we're able to, I don't know what that point's doing. It gives us a relationship that we're able to solve some mathematical things. So if I knew a distance from this edge to the centroid, and then I wanted the distance from the centroid to this vertex, I would know that there's going to be a relationship. I guess not between those two, sorry. Between, like, if I knew the distance from the edge to the centroid is 2, then I know from the edge to the other vertex is 6. I know that 1 to 3 or 2 to 3 relationship, where it's 1/3 from all the sides. And that's not just true for this long one, it's true for all 3. So if we were to do this one, it won't be a nice pretty number, but that's 1.32316. So that's 1/3 of this total median. So this one should be double that. 2.643. Yep, so that's double that one. Alright, I've made it angry. So recapping this one, our special segments are medians. The point of concurrency is called the centroid, or outside of math, the center of gravity or center of mass. And then the mathematical significance, or what we can do in equations, is it's located 2/3 of the way from any vertex to the opposite side, or 1/3 of the way from the side to the opposite vertex, right? It's a basically 1 to 2 ratio. So the distance from here to here is half of the distance from here to here. And that goes into a lot of engineering calculations. It's a really useful thing. Okay, so fourth one, the final special segment we're going to look at. This one is, to me, the most kind of like nebulous. I think there are some significant things to it. I'll have to kind of look into more what they are. For now, let's just talk about what it is. So we have this triangle, and okay, I can still change it. So in this triangle, each of these special segments is drawn from the vertex to the opposite side. But this time, we're not going to the middle of the opposite side, we're going the shortest path possible. So we're drawing a perpendicular line from this corner to this side. So this special segment, let's make this horizontal, or near horizontal. I don't want it to be horizontal. Okay. So now you can see if this is basically horizontal, this is basically vertical, right? They're perpendicular to each other. So this one is what you think of as being the height of the triangle. So if we wanted to find the area of this triangle, we would multiply the base times the height and divide by 2. So this is an important segment because it's the height of the triangle. It lets us find areas, but we don't call it a height because there's 3 of them, and not all of them there's not always vertical. So height is kind of a lower level word. The technical term for this is an altitude. So it means that if you're going from a flat side straight up, that's the height of it. It doesn't matter whether that flat side is horizontal or not. So these 3 things are called altitudes, and they go from a vertex perpendicular all the way to the opposite side. But I think of it, look at this like a mountain. That's like the height of it, and we call the height something as an altitude. Like if you're up on a high mountain or in a plain, that's your altitude. So it's the distance straight up to the vertex from any side. Okay, so that's kind of its significance already, is that it's the height of the triangle. We use it in area formulas. But some other things about it, this point of concurrency is called the orthocenter. So orthocenter, to me, like I said, is the most like nebulous of the four. But let's look at some properties of it. So kind of like the circumcenter that we looked at first, in an acute triangle, this will always be inside the triangle. So if I keep this triangle to have 3 acute angles, the orthocenter stays inside of the shape. But, kind of like the other one as well, if I make this an obtuse triangle, so I basically flatten it out, then the 3 lines meet outside of the triangle. And I don't actually know if this has anything to do with anything, but it looks like focusing lines, right? It looks like you're kind of like a prism taking lines and focusing on a point out here that is perpendicular to all 3 vertices of a triangle. And maybe that has some significance in something like optics or something I'm not too familiar with. But it's a similar idea to what we saw up here. But the difference is, notice that this focal point, right, this circumcenter, is located basically outside of this obtuse side, right? So it's kind of projected out from the flat side, whereas this one looks like it's projected out from the vertex across from the obtuse side. So it's basically like behind the triangle instead of in front of it, is how I'm thinking of it if the triangle was like a bowl shape. So that's the similar thing between the two, right? So those two, your point of concurrency can be inside or outside the triangle, just depending on whether it's acute or obtuse. This triangle doesn't want to behave anymore. I think I maybe added a constraint I didn't mean to. Oh, that works. Okay. So acute triangles, it's inside, obtuse, it's outside. Here, we didn't really look at that, but no matter how I change this triangle, since we said that this centroid has to be 1/3 of the way between the side and the vertex, there's no way for it to ever go outside the triangle. If I made this closer and closer to basically almost not even be a triangle, that centroid is still inside of the shape. Similar thing with the InCenter. Since it's the inscribed circle, it has to remain inside the triangle. There is no way for it to ever go outside of it. So I could make this an obtuse, skinny triangle somehow. It doesn't want to change correctly. Man, this one doesn't want to do a thing. Anyway, so you get the idea that if I make this, there we go. If I make this obtuse, this InCenter still stays inside the circle no matter what. It cannot go outside of it. But on the other two, the circumcenter and the orthocenter, are allowed to go outside of the triangle. So if, also like the circumcenter, if I make this a right triangle, then the orthocenter is right on the triangle. But there's a slight difference. So the orthocenter meets at the corner of the right angle for a right triangle, whereas in a right triangle here, we saw that the circumcenter lies at the center or the midpoint of the hypotenuse. So for right triangles, there's a couple of extra relationships for these two, where the circumcenter is the midpoint of the hypotenuse, and the orthocenter is the vertex of the right angle. Yeah, so other than the right triangle thing, I don't know of any other mathematical relationship that we're getting from the orthocenter. So if there's another one, I'll be sure and talk about that in class. But man, this triangle is being all wonky. Let's undo that. I think I just made it way too small. Okay. So I've got my triangle back, and I've got, I see, this is, sorry, I'm fixing this right now. I'm going to make that there. That way they'll come together. There we go. I've got it back. So the last thing I want to talk about in this section, so let's recap this one. We had these lines are called altitudes. They're like the height of the triangle, so they go from the vertex perpendicular to the other side, opposite side. We have this point called the orthocenter, where the three altitudes meet. And then we know that it can be inside or outside of the triangle, depending on whether it's acute or obtuse. Or for a right triangle, it lies on the vertex of the right angle. So those are our things for the orthocenter. But the last thing I want to look at is what happens if we make an equilateral triangle. So I hope that I haven't added any extra constraints as I was messing around with these, but let's see. So I'm going to delete my circumcircle. I'm going to delete my InCircle. And we're just going to leave these segments. I feel like I've added something I didn't want to add. This should not be horizontal. Are you free to move again? Let me pause for 1 second and fix this. Okay, so I think I've got it undone to where it is free to move again. I must have created some constraint I didn't want as I was moving stuff around. That is a frustrating thing sometimes, is that like if I try to move something here, see it's trying to create a vertical constraint between those. I have to be careful as I move stuff not to create stuff like that. So if you're trying this out yourself, you'll need to be careful of that and watch out for that. Okay, so the last thing I wanted to look at is what happens if these are equilateral triangles. So we can kind of see as this gets toward being close to equilateral that these four centers, these 4 points of concurrency, are all kind of right in what looks like the middle of the triangle. And it turns out that if we have a perfect equilateral triangle, then all 4 of these points of concurrency are the same exact point. So you could have a problem with an equilateral triangle that basically gives you information about the orthocenter, and then you would also know that that is the circumcenter and the InCenter and the centroid, that it's the same for all 4. So that if we knew this is an equilateral triangle, and we knew that a certain point is the orthocenter, even though that has to do with altitudes, it would give us the same mathematical relationships as the others. Like on this one, we had that the distance to each of the sides, perpendicular distance, was the same, or the distance to each vertex is the same. So those will all be true if we have an equilateral triangle. All 4 points of concurrency occur at once. And then the last thing is looking at if we have, I need to get rid of this triangle. If we have a regular polygon, so an equilateral triangle is a regular polygon for triangles. So if I have this shape, then we know that the circumcenter, the circumscribed circle, and the InCircle have the same center, right? They're the same. And what I want you to see here is that that relationship stays the same for all regular polygons. So if we increase the number of sides to like 5, then the circle drawn around the shape and inside the shape remains the same center. In fact, in a program like OnShape, when you go to draw a polygon, if I want to draw a regular polygon, I have to specify if I want to draw it by its inscribed radius or its circumscribed radius. So if I draw an inscribed polygon, then the dimension that I'm defining is going to be the radius or the diameter of that circle inside of the shape. Whereas if I draw a circumscribed one, it's going to be the opposite. I'm going to be defining, let's keep that at 6. I'm going to be defining the radius or diameter of the circumscribed circle. So that's the way that regular polygons are generally sized, even though we often think of a side length as being the defining characteristic. In a drafting program like this, the radius is actually what's usually used to define the shape. So we've talked about our points of concurrency. This last topic of regular polygons is a little extended beyond what we're doing with triangles right now, but I think it is an interesting thing, especially since we're in an engineering program, to let you see that that is how we define regular polygons. And remember, this is regular polygons. We can't make something like this if it's not regular. So if you think about this pentagon, yeah, it's a pentagon, but there's no way to make an inscribed circle because we saw that circles require 3 points. So I could make this tangent to 3 of the sides, but there's no way to make it tangent to all 5 of the sides unless it's regular. So I can make that tangent to those 3. If I try to make it tangent to the other 2, it's just going to pull in the shape and make it a regular pentagon. So this idea of circumscribed and inscribed regular polygons does not work unless the shape is regular. Triangles are special and have these InCenter and Circumcenter and all that no matter what, just because they're 3-sided shapes. And those 3 points are what we need to make a circle. So a triangle, I know we were just seeing that in the other section, but just to make sure we really see that here, a triangle, no matter what, I can always make an inscribed circle, no matter what shape the triangle is, because I just am saying it's going to touch at 3 points. I missed that being coincident. There we go. So, yeah, that's kind of our thing on points of concurrency. Hopefully you've got a good idea of all of our vocabulary, what these special segments are called, what the points of concurrency are, and what the mathematical value of